as was mentioned in my previous video, we're going to try to find closed form expressions for summations that look kind of like known summations. This one, if you look, is a quadratic, which in some sense should look like that I squared summation I wrote down before. So how on earth are we going to do that? We're going to use those properties we mentioned in the past and try to exploit them to analyze the summation. So one of the properties we had in the past was what we called linearity. We can distribute the summation. I can distribute it across the addition, and I can factor out constants. So I can write this as 2 times the summation from I equals 1 to n of I squared plus 3 times the sum from I equals 1 to n of I plus the sum from I equals 1 to n of 5. You might ask, well, why on earth didn't you factor out the 5 in the last summation? You could. However, I'd find it a little awkward to have 5 times the summation of 1. So instead of doing that, I've just left the 5 inside of the summation. Now, 2 of these summations we have seen already. This summation I'm highlighting in purple, and similarly for the summation I'll highlight in green. We have formulas for those. Let's comment on them off to the side. So we have the following summation formulas. That the sum from I equals 1 to n of I squared was equal to n times n plus 1 times 2n plus 1 all divided by 6. And similarly, we had a formula for the sum from I equals 1 to n. We proved that formula actually, so this goes 1 to n of I is equal to n times n plus 1 divided by 2. Let us use both of those formulas and see what we get. So this is equal to 2 times, using that first formula, we have n times n plus 1 times 2n plus 1 divided by 6. Plus 3 times using the second formula, which is n times n plus 1 divided by 2. Plus, that last summation, we didn't have a formula for that. However, it's a very easy summation. Remember, in the very beginning, we talked about the number of terms in a summation. The number of terms is the top bound minus the bottom bound plus 1. And the inside of that summation is constant. That's 5 plus 5 plus 5 plus 5. By definition of addition, if you're adding up a number a certain number of times, that is the same as multiplying it by the number of times you're adding it up. So the number of times we're adding it up is the top bound of the summation minus the bottom bound of the summation plus 1 times the sum and the thing inside of the summation. Notice this will always occur if the summation index, I in this case, does not appear inside of the summation. That quantity is for all purposes constant. So you can multiply the inside of the summation by the number of terms of the summation. I can simplify this by getting rid of the minus 1 and the plus 1 and writing it as 5n. We could further simplify this and try to find a nice, sweet closed form expression. However, it didn't ask us to simplify or anything. It just said, find a closed form expression. This is a closed form expression. The difference between the first formula and this formula is that in order to compute the value, all I need to do is plug in n and do basic arithmetic, adding, multiplying, and dividing here. That's all I need to do. However, in the first one, I needed to use a summation and actually write something like a for loop to compute the value. This is a much faster computation to compute than the original given expression. So the value of this expression is that now, rather than having to actually add up those numbers, you could just plug into this formula. If you're trying to min-max this, you could theoretically try and simplify this and minimize the total number of operations or something, but we are not so interested in that.